This is section 2.5, the second part. We've started this section already. We worked a bit with a few examples and so on. We looked a little at the equation AX equals B, where the X and the B are both capital letters standing for matrices. We're going to work a bit more with that now. So let's take a look. Section 2.5, second part, the matrix equation AX equals B. Now here, if you remember, A is still the coefficient matrix. X and B, though, now are also matrices. X is the solution matrix. B is going to be a matrix of constants. Okay, here's an example. Suppose we know that A times B is equal to C, and C is made up of C1, C2, and C3. And suppose we also know that A times 1, 1 is equal to C1, A times 3, 4 is equal to C2, and A times negative 1, 7 is equal to C3. And our instructions are now to find B. Okay, well, we know that A times B is equal to C. We know C is made up of C1, C2, and C3. So B is just going to be 1, 1 in the first column, 3, 4 in the second column, and negative 1, 7 in the third column. That's because A times the first column of B has to be the first column of C. A times the second column of B has to be the second column of C, and A times the third column of B has to be the third column of C. We had a theorem in the first part of the lecture that mentioned if we have A times X, that would be A times the first column of X, A times the second column of X, and so on. Well, from that theorem, if A times X is equal to B, where X is made up of columns X1, X2, and so on, that can be rewritten as AX1, AX2, etc., up to AXQ is equal to B1, B2, up to BQ. Now, if we match up each of those entries, we have Q linear systems. Keep in mind that each of the X1 and B1s, those are vectors. So we have AX1 is equal to B1. That's a linear system. We also have AX2 is equal to B2, all the way up to AXQ is equal to BQ. So AX equals capital B, A capital X equals capital B, is actually referring to Q linear systems. Okay, let's look back at the type of example we would have seen in the previous section, section 2.4. Solve A little x equals little b for A equal to the matrix consisting of 1, 0, 2 in the first row, 0, 2, negative 2 in the second row, and negative 1, 1, negative 2 in the third. Suppose we also want initially our little b to be 1, 2, 1. Then we want to redo this problem for little b equal to 7, negative 4, negative 4. And then again for little b equal to 9, negative 10, negative 10. So I'm actually asking you to solve 3 systems of equations which all have the same coefficients, the same coefficient matrix. Okay, now you remember how we solve systems of equations. You make an augmented matrix and you reduce the matrix. So I would want to put the A on the left, the 1, 0, 2, 0, 2, negative 2, negative 1, 1, negative 2 on the left, and then that first B, 1, 2, 1 on the right. Those are my constants. And you remember that's how we make an augmented matrix. Okay, well, I initially need to get rid of this negative 1 in the bottom row. I need for that to be a 0. So if we'll do row 3 plus row 1, that'll take care of that. That gives us across the bottom row 0, 1, 0, 2. Okay, next, I have a 2 in the second row that I want to be a 1. Now, there are a couple ways you can go about making that 2 a 1. You could take half of the row if you wanted. You could also, if you happen to notice there's a 1 right below it, just make the switch, row 2 switch with row 3. And that's what I chose to do because I don't really like a lot of arithmetic if I can avoid it. Okay, so row 2 switch with row 3 is what we're going to do next. That's going to make your second row 0, 1, 0, 2. And then the bottom row is 0, 2, negative 2, 2. All right, at this point, I want to get rid of that 2 in the bottom row. I need for that to be a 0. Okay, so if we will then do row 3 minus 2 row 2, that'll make that entry a 0. The only thing that changes here is row 3. So across the bottom row, I now have 0, 0, negative 2, negative 2. Okay, where that first negative 2 is in the bottom row, I need for that to be a 1. So if we'll do negative 1/2 row 3, that'll make that negative 2 a 1. It'll also make the negative 2 beside of it a 1. So now across the bottom row, I have 0, 0, 1, 1. We're almost finished. On the top row, there's a 2 that I want to be a 0. So if we'll do row 1 minus 2 row 3, that'll accomplish making that 2 a 0. Okay, so now across the top row, I have 1, 0, 0, negative 1. And if you see, the whole left side is reduced down to the identity matrix I sub 3. That means that what is on the right, the negative 1, 2, 1, is my solution. That little x that I was looking for. Negative 1, 2, 1 is my solution. So x sub 1 would be negative 1, x sub 2 would be 2, and x sub 3 is 1 if I'm looking for the particular variables. Okay, now we also had a second part and a third part to this, and we went through all this work for just the first part. Let's see what's going to happen when we start the second part. Again, we want to make an augmented matrix and reduce. So start by putting your A matrix, your coefficients on the left, the constants on the right. Here we have different constants, 7, negative 4, negative 4. That was the little b that we had in the second part. Okay, well you see again, in that third row I have a negative 1 I need to get rid of. What's going to do it? Well, row 3 plus row 1. Does that seem a little bit familiar? Okay, then after we do row 3 plus row 1, we get this matrix. So the bottom row now is 0, 1, 0, 3. I need for, in the 2, 2 position, second row, second column, that 2, I need for that to be a 1. So again, because I don't like a lot of arithmetic, I'm going to want to do row 2 switch with row 3. Now, those were the same 2 steps that we started with in the last problem. Do they seem familiar? Well, they should. It's exactly what we did last time. Row 3 plus row 1 was our first step. Row 2 switch with row 3 was our second. You think that's coincidence? No, never. So why was it the same? Well, it's because we reduce a matrix based on the left side. Those coefficients didn't change from part 1 to part 2. Since the coefficients didn't change, we'll just do the same steps over again for part 2 as we did in part 1. And we'll do those same steps over again for part 3 that we did in part 1. But we can work smart. We can solve all 3 parts simultaneously. Here's how. Instead of just making an augmented matrix with the 1, 2, 1 on the right-hand side, or the 7, negative 4 on the right-hand side, or the 9, negative 10 on the right-hand side, why not throw them all over there? So I've got, after the line, I've got 1, 2, 1, and then 7, negative 4, and then 9, negative 10. What this is going to accomplish for me is it's going to solve all 3 of the systems of equations simultaneously. Let's see if we really believe this is going to happen. Okay, I start again, same old first step, row 3 plus row 1. Okay, that's because I had a negative 1 in the bottom row that I needed to be a 0. Once we do that, across the bottom row now I have 0, 1, 0, and then 2, 3, negative 1. That's our bottom row. Okay, just like before, where there's a 2 in the second row, I need for that to be a 1. My step before that I chose to do was row 2 switch with row 3. Well, let's look. Row 2 switch with row 3. Hey, no surprises there. Okay, once you switch those two rows, you'll see that your second row going all the way across is 0, 1, 0, 2, 3, negative 1. But as changes are occurring to the left-hand side, changes are occurring to the right-hand side. Okay, next, in the third row, I have a 2 where I need to have a 0. If we will do row 3 minus 2 row 2, that'll fix that too. Okay, now going across the third row, we have 0, 0, negative 2, negative 2, negative 10, negative 8. All right, where I have that first negative 2 in the third row, I need for that to be a 1. And last time we chose to do negative 1/2 of that row. Again, no surprises, same steps. Negative 1/2 of row 3. That's going to change that negative 2 in the 3, 3 position into a 1. So now our third row is 0, 0, 1, 1, 5, 4. Almost done. In the first row, you'll notice I have a 2 where I need to have a 0. So if we will do row 1 minus 2 row 3, that'll give us a 0 right there. Okay, so now you see on the left-hand side I have 1, 0, 0, and then 0, 1, 0, and then 0, 0, 1. That's row reduced. It's reduced echelon form. On the right-hand side, you see that matrix looks completely different from the matrix we started with on the right-hand side before. Okay, if we take a look a little more closely at that matrix, you'll see that on the left-hand side, not only is that reduced echelon form, it's the identity matrix, I sub 3. In the first column after the line, that was where we put that 1, 2, 1, which was the constants for the first system of equations. So that now, the negative 1, 2, 1 is the solution we got to the first part. In that second column, we put the constants for the second part. So now we have, in this matrix, the solution to the second part. And in the third column after the line, we put the constants for the third part, so now we have the solution to the third part. Now we could have done a much larger matrix. We could have done several systems of equations. We could have done like 15 systems if we'd wanted to. We would have just had more and more and more columns, you know, but let's not do that. Okay, so to solve AX equals B, where A was the matrix 1, 0, 2, 0, 2, negative 2 in the second row, and in the third row, negative 1, 1, negative 2, and where B was the matrix, you notice those columns. The first column is 1, 2, 1. That was the first part, the little b that we used. The second column, 7, negative 4, negative 4, that was the little b that we used for the second part. And 9, negative 10 was the little b for the third part. So to solve A capital X equals capital B, what did we do? Well, we put A on the left and capital B on the right. And when we finished, we had I on the left, the identity matrix, and X, our solution matrix, on the right. Okay, that concludes section 2.5. As you saw, to solve AX equals B, where X and B are both matrices, we reduced A on the left and B on the right. And when we finished, we had I on the left and X on the right. Our solution was on the right. If you can't get I on the left, that often will mean that there's no solution. Now, not every time, and here's why. Sometimes that X matrix that you're looking for is not a perfect square matrix like the example that I showed. Sometimes you might be looking for an X matrix that's, say, maybe a 3 by 2 matrix or a 2 by 3 matrix or something crazy like that. And in those cases, you'll sometimes get a row of zeros across the bottom or something strange like that, which might lead you to think, hey, I can't get a solution, but there it is staring at you. So you just need to practice with these a bit and do some homework problems. There's some very good problems in the homework, and give those a shot, and then you'll see all those strange things that I mentioned.